Hey everyone, who's ready for some multi-cloud monitoring and digital forensics? Yeah, I know that sounds pretty complicated, but I promise it's really not nearly as complicated as it sounds. In 2020, IBM and the Ponemon Institute found that the average cost of a data breach was $3.86 million. As terrible as that sounds, it actually gets worse when you think about it. That is an average number, meaning that there are many smaller scale breaches that drove this number down. If you work for a larger organization, this could easily cost you 9 figures. So how are we going to save your organization from the fate of a massive breach? Welcome to multi-cloud anomaly detection, finding threats among us in the big 3 clouds. My name is Brandon Evans. I am a certified instructor for the SANS Institute. I am the lead author of SANS Sec 510, Public Cloud Security, AWS, Azure, and GCP, a course that explores many of the topics we will discuss today and which has a brand new GIAC certification called GIAC Public Cloud Security, or GPCS. Like most SANS instructors, SANS is not my day job. Most days, I am a practitioner of security in the field. I am proud to have recently joined Zoom Video Communications, where I lead the internal application security training program for one of the most consequential companies in the new world we live in. I hope that this presentation will deliver happiness to you by equipping you with the tools and skills you need in order to protect your organization's data and assets in the cloud. So, if we know that there are countless threats in our cloud virtual networks, why are they so hard to find? Unfortunately, there are many imposters among us. The traffic and logs they generate look identical to that of normal users, but behind their facade, they are pilfering your resources and exfiltrating your data. The less sophisticated attacker of yesteryear would transfer your data over relatively conspicuous channels such as FTP. Today, they can use seemingly innocuous protocols that aren't designed for mass data transfer, such as DNS. Worse yet, if the attacker can export your cloud credentials, they can pull your data from outside your private network by making valid requests to your cloud's APIs. Is it possible to find a few malicious communications in an ocean of legitimate ones? The answer is yes, but it's also very difficult. So, we throw millions of dollars at intrusion detection and data loss protection tools. Now, don't get me wrong, the cost of getting breached far outweighs the cost of procuring these tools. But what if there was a third option? What if I told you that you could detect intrusions and prevent data loss with your cloud provider's native services? Think about it. The cloud generates so much data. Nearly every action taken in the cloud can be logged. If we can detect anomalies in these logs, we can identify indicators of compromise. The big 3 cloud providers give us all the tools we need to do so. Unfortunately, if organizations fail to use these tools at their disposal, they are unfortunately useless. If you aren't using these tools or don't know what I'm talking about, you're in the right place. This session will teach defenders how to unlock the full potential of the audit logs generated by the big 3 cloud providers: Amazon Web Services, Microsoft Azure, and the Google Cloud Platform. We will focus on 2 types of audit logs: cloud API activity logs and network flow logs. Using a real cloud environment, we will demonstrate how to detect 2 types of attack signatures by looking for anomalies in these logs. While manual log analysis is helpful, it is also expensive. So we will also discuss how to generate alerts from these logs. These alerts can tip off our incident response teams of potential indicators of compromise. Finally, while each cloud provider has relatively similar logging services and concepts, there are some key differences that you must be aware of in order to use them properly. We will explore these differences in depth. So let's start by talking about cloud network flow logging. What is flow logging? It is a powerful tool for monitoring a network. Flow logging captures metadata about the traffic flowing to and from a network. We specify that this is metadata because flow logging does not actually capture the contents of the network traffic, which can be highly sensitive, like credit card information or social security numbers. Instead, as we will see shortly, flow logs just tell us where traffic is coming from, where it is going, how much of the data is being transferred, and a couple other pieces of data. This alone can be very useful. If a particular set of IP addresses are sending anomalous amounts of data or are probing unexpected ports, this is a good sign that these IP addresses might be controlled by threat actors. If we see a large amount of data being sent from our network to a particular host, this might indicate that our data is being exfiltrated. We can glean a lot of information from this data. Now, flow logging is a common practice on premises, so it shouldn't be surprising that each of the cloud providers support it as well. Here's the catch. None of the big three cloud providers have flow logging enabled by default. The customer must explicitly opt in and define a log retention policy. So if your organization hasn't done this already, make sure you enable flow logging immediately. Once flow logging is enabled, we can persist, view, and analyze the logs using a variety of cloud services. We will discuss each related service for each of the cloud providers in scope. Thankfully, our friends at the Center for Internet Security provide guidance on this exact topic. For each cloud provider, they detail how to properly use their cloud flow logging services. For AWS, we must ensure that flow logging is enabled for each virtual private cloud or VPC. In their view, it is sufficient to only capture metadata about packets that are rejected by your security groups and network access control lists. For our purposes, it is hard to understand what anomalous traffic looks like without establishing a baseline. Therefore, we recommend that you capture all flow logs for all packets. Now, regardless, we have to define how long we want to retain these logs. Sadly, on average, it takes 210 days for an organization to discover that it has been breached. Therefore, the CIS suggests that organizations retain their flow logs for at least 1 year. But as you can imagine, this can get very expensive. Amazon CloudWatch, one of the best services for analyzing logs in AWS, is also the service with the highest storage cost. Luckily, you don't necessarily need to store your logs in CloudWatch for 1 year. Instead, you could retain your logs in CloudWatch for a smaller period of time before archiving them into cheaper storage services like S3 and Glacier. In AWS, the services used to manage internal traffic, aggregate flow logs, and analyze logs are all different. This slide shows how these services work together. As mentioned on the previous slide, we must enable flow logging on individual VPCs. Alternatively, we could enable them on subnets within the VPC or in an individual Elastic Network Interface or ENI. To analyze the logs, we will need to use Amazon CloudWatch Logs, which provides a general purpose mechanism for querying logs. We will use CloudWatch extensively throughout this presentation. And there is a delay between the traffic, before the traffic is aggregated, there is a delay between when traffic is received. By default, flow logs are aggregated on a 10-minute interval and sent to CloudWatch on a 5-minute interval. You can reduce these intervals to 1 and 5 respectively. With that configuration, you can confidently rely on your logs showing up between 1 and 6 minutes after the traffic has arrived to your network interface. Let's talk about a sample flow log captured in a VPC and queried through CloudWatch Logs. There's a lot of metadata that we can see here, but remember, the actual data is not persisted. Instead, we can just learn where the traffic is coming from, where it's going, how is it being delivered, how large the message is, and whether or not the data was accepted by our network rules or rejected. We can query and visualize these flow logs in a few ways. For automation purposes, it is important to know how to query them from the command line interface. You can see the syntax for doing this on the left-hand side of this slide. It is a two-part process. First, you initialize the query, and then you get the results. AWS splits these steps up because these queries can take a long time to run, and you might want to see the partial set of results before the query is completed. Now, for the folks who are more visually inclined, AWS also provides a graphical user interface for running these queries in the AWS console. An additional perk of this method is you can visualize the traffic patterns. In this example, we are looking for rejected traffic from one of our virtual machines. An analyst can view the time-lapse bar and find periods when the rejected traffic spiked or dipped from the baseline. The CIS provides very similar guidelines for flow logging in Azure. In Azure, the network resources are logically isolated into virtual networks, or VNets, instead of VPCs, but it's the same concept. Traffic within a VNet is controlled by network security groups, or NSGs. We enable flow logs at the NSG level in Azure. Azure Flow Logs, when enabled, always captures both accepted and rejected packets. So we don't have to worry about that particular configuration like we did for Amazon. Still, we need to ensure that we persist the logs for a sufficient amount of time. Oddly enough, the CIS differs from the guidance for AWS by recommending a retention period of at least 90 days. For consistency, we are going to recommend that you persist them all for at least 1 year, just like we said for AWS. Like with AWS, Azure requires multiple services to use flow logs. There are a lot of moving parts here. First, you need a VNet with an NSG. Then you need to enable the Network Watcher service in your VNet to start sending flow logs to an Azure storage account. For those who aren't familiar, Azure Storage is Azure's general purpose file storage service, kind of like Amazon S3. Azure uses Azure Storage behind the scenes all across their service catalog. Now, technically, you could read the flow logs directly from Azure Storage, but it's not query. It's not pretty. You can't query it. It is much easier to analyze them using an Azure Log Analytics workspace. This interface exposes the logs to be queried through the Custo Query Language, or KQL. Like with AWS, Azure Flow Logs are not available for querying immediately. You can aggregate them to your Log Analytics workspace either every 10 minutes or every 60 minutes. So when compared to the other providers, these are the slowest aggregation options. Now, for the longest time, I thought that Log Analytics could only be queried via the Azure portal. Eventually, I figured out that you could install an extension for the Azure CLI. If you want a visualization, though, the portal is the way to go. The first time I queried Azure's flow logs, I assumed that I did something wrong. I was getting far less results than I was getting in AWS. And as Ben Allen, another course author at SANS, often says, when it comes to flow logs, quote, quiet is actionable. Either you've lost internet connectivity or your monitoring tools have failed, end of quote. There's no way that my VM was only receiving a few messages every hour. I eventually realized that Azure's flow log records aggregate the traffic. A single record can represent tens or hundreds of similar messages. So make sure to examine each record to determine the flow count. In this example, we are graphing the flow count associated with the query over time. Here's an example of how we can use Azure Log Analytics' CLI extension to query flow logs. The data here is very similar to what we have in AWS. Finally, on to GCP. Like AWS, they call their private networks VPCs. We must enable flow logging at the subnetwork or subnet level. Now, one thing to be aware of with GCP is that they have a sampling rate. You can sample a percentage of the flow logs instead of all of the flow logs of a certain type. This might be useful in reducing storage costs, but at the same time, you might regret having missed data in the event of a breach. So we recommend sampling 100% of the logs. Now, if you configure Google Cloud Logging to include all metadata in its flow logs, you can get a lot of information. And we could talk about several of the items on the slide. But what is most important is what the logs don't include, an indication of whether or not the traffic was accepted or rejected by the firewall. You might be thinking, wow, that's a huge oversight from Google. When are they going to fix this bug? Well, the answer is it's not a bug. It's a feature. This is by design. Why? Because the GCP flow logs for the VPC cover traffic from, quote, the perspective of the VM. This means that packets will be logged as they enter and exit a virtual machine, regardless of how they are handled by the firewall. So we will lose all of the messages that are blocked by the firewall inbound, and we will have no indication of whether or not the traffic is accepted outbound. The outbound flow logs will contain a lot of extra data, and we will have zero visibility into the inbound traffic because those packets will never make it to the VM. This is a huge distinction between GCP and the other two providers. Now, for this reason, you might want to consider also enabling firewall rules logging. This allows you to audit your firewall rules and detect traffic that is denied at the firewall level. You can read more about this feature at this URL. But hopefully, you now understand the different types of flow logging in GCP and which types are appropriate for your organization. Now, GCP is unique in that it is the only provider that uses a single service for persisting and querying logs, Google Cloud Logging. It's kind of convenient. You don't have to manage multiple services here. This service can be queried via the CLI and the GUI as shown here. In our first demonstration, we are going to audit our flow logs in each cloud environment in order to reveal that our organization has been compromised from the inside. Before we get into it, let's talk about supply chain attacks. We've all heard about the SolarWinds supply chain attack that happened last year. It is scary to know that the services used in our environment can be compromised. What scares me even more is the thought about an open source component being compromised. Modern applications are composed of thousands of third-party components. How can we know that each of these components are clean? The answer? We can't. Our industry has failed time and time again to this unsophisticated but powerful attack. One particularly incredible example of this to me was in July of 2018, when ESLint, a popular and simple utility for cleaning up Node.js code, was compromised. The attacker embedded malware into the library that downloaded another snippet of malware from pastebin.com. It would then execute this malware every time ESLint ran a scan. At minimum, this resulted in the theft of countless access tokens for npmjs.com. It seems like the attacker wanted to get these credentials to publish even more malware and spread endlessly. Fortunately, npmjs.com quickly revoked all tokens generated on or before the date of compromise. Unfortunately, this also broke a lot of builds and made a lot of developers very unhappy that day, speaking from experience. This slide just is an example of the different types of supply chain repositories out there. In our presentation, we will examine a piece of malware from npmjs.com that has found its way into our clouds. You might have noticed that earlier in this presentation, there were a couple signs of malware in our flow logs. If you noticed some anomalies in the screenshots we provided, congratulations, you have the attention to detail and the curiosity that is necessary in order to detect things like this. So, are you ready to log? Let's get into it. In our demo environment, we have a real application for a fake medical company named Nimbus Immutabile. This application has been deployed to AWS, Azure, and GCP. Each version of the application uses the cloud-native services for that provider. Now, these applications were written in Node.js, a popular runtime for running JavaScript on the backend. And for those who are not familiar with Node.js, its package manager or its supply chain is called NPM, the Node Package Manager. And if we want to look at the packages used by this application, we can simply look at the package.json file. Now, if you look at this file for a bit, you'll notice that one of these things is not like the other. One of these packages looks very suspicious. Check read stream, really awesome, totally secure, I think. This is a real package that we deployed to npmjs.com. You could download it right now. I wouldn't recommend it because it's doing something nefarious. If we look at the source code, we'll see that initially it looks like this code is actually useful. But at the very end, we'll see that it's requiring this other file named innocuous. Is the innocuous file actually innocuous? Of course not. It has some obfuscated malware in it. This was the attacker trying to pull one over on us. And we can't tell what this code is actually doing. That's the purpose of obfuscation. But perhaps we could figure out what this code is doing by looking at the network traffic that it is generating. So we have our flow logs enabled in our cloud providers. Let's take a look at AWS first. Here we are running a query that is looking at the traffic from our AWS EC2 instance and it's looking for rejected traffic specifically. So we're going to run this query. After it's done, we can look at the results. And we'll notice that there's a lot of traffic being sent on port 9999, which is not a typical port for sending or receiving data. Now, if we look at the same thing in GCP, this is a little bit more of a complicated query, but we are able to detect the same kind of data. But as mentioned earlier, VPC flow logs do not tell you whether or not a packet was accepted or rejected. That's at the firewall level, not at the VM level. So to do the same basic thing, we're going to look for traffic over ports that we are blocking, that we know is not going to make it through the firewall on port 80, 443, and 3306. So once we run this query, we're going to see some similar results to what we had before. A lot of traffic being sent over port 9999. So flow logs only shows you metadata about traffic. It doesn't show you the contents of the traffic. To do that, we could go to the virtual machine over SSH, and we could run a utility like TCP dump, which is going to show us all of the traffic over port 9999 outbound. And in a short moment, we're going to see something suspicious. So here we can see some traffic that looks suspicious. This is a DNS query, but it doesn't look like a normal DNS query. It looks like this message might be encoded. So if I copy this message right here, maybe, just maybe, I'm going to do this again. Sorry about that. So after a while, we will see this DNS query right here. This doesn't look like a normal DNS query. It looks like potentially an encoded message, perhaps using base 32 encoding. So if I copy this message and I join it with this message, because DNS queries can only carry 63 characters, then I uppercase it and I base 32 decode it, we will see that this message contains the MAC addresses for the Nimbus Immutable virtual machine. Now, MAC addresses are private. You can't determine what a MAC address is from the outside, but it's also innocuous. This is something that we're doing for an example. Imagine if instead we were getting credit card numbers, social security numbers, API keys, other data that is only accessible by your virtual machine. This goes to show that data could be exfiltrated via malware like the one that we demonstrated, and that we can catch things like this by looking for anomalies in our flow logs. So we've seen the 3 cloud providers logging solutions. What are the core takeaways in terms of the differences between these 3 solutions? The first thing that you need to be aware of is the similarity. None of these logging solutions are enabled by default. So if you take nothing else away from this section, enable them today. We've talked about the delay between triggering the logs and getting the logs into a queryable format. GCP is the fastest, Azure is the slowest. In terms of retention period, AWS and Azure, they allow you to have your logs stored indefinitely. Of course they do. They can charge money for it. So I don't know why they would have any restrictions. Interestingly enough, GCP does have a restriction, but it's absurdly high. It's 10 years. So I think you're good to go after 10 years. I don't think this is really a functional difference. After 10 years, your flow logs are probably not useful to you. And if they are, back them up to an external service. In terms of command line support, all 3 of them support the command line, but Azure requires an extension. And finally, the most important distinction in terms of analyzing the logs is AWS and Azure allow you to look at blocked ingress traffic, whereas GCP, unless you're using firewall flow logging, you will not see any data about the ingress traffic that has been rejected. So very critical difference here. Now let's talk about cloud API logging. There are a lot of services in the cloud. We need to interact with these services, sometimes as administrators and other times as users. The rules that dictate how we interact with cloud services are defined in Cloud Identity and Access Management Services, or IAM. IAM services allow you to grant permissions to both individual users and to cloud infrastructure. For an example of the latter, when you want to grant your application access to a cloud resource, such as Amazon DynamoDB, you can provide the VM running the application permissions with what is called the instance profile role. The diagram on this slide illustrates the flow from start to finish. We're going to make a request to DynamoDB using a request signed with our IAM credentials. We are going to then analyze, does this entity, does this principal have permission to perform this action on this resource? If the answer is yes, we're going to get the results. If not, we are going to throw an error. So it is important to understand that if the credentials used in the background with the cloud IAM service are compromised, the attacker will have all of the privileges granted to that IAM principal. An attack just like this happened to Capital One in July of 2019. A sophisticated attacker who had previously worked for AWS knew that it was possible to extract the IAM credentials for a VM hosted on an Amazon EC2 instance that is hosting an open forward proxy. Normally, a proxy will accept requests to users to fetch a particular resource on their behalf. If the proxy accepts any URL, it is possible to fetch private resources within the VM's private network. This is called a server-side request forgery vulnerability, or an SSRF vulnerability. In Capital One's case, the attacker was able to use such a vulnerability to have the proxy server access the internal instance metadata service on the EC2 instance, which contains the instance's IAM credentials. Thinking that this is a valid request because the application has no way of distinguishing between fetching a legitimate file and an illegitimate file, the proxy returned the credentials to the attacker. From there, they were able to access all of the resources that the EC2 instance had access to. Unfortunately, this included S3 buckets containing 100 million credit card applications. So there are a lot of ways to prevent attacks like this. You could eliminate the SSRF vulnerability. You could reduce the permissions so that your EC2 instance doesn't have access to all this excess data. There's a lot of things you can do to prevent these attacks. But this is a discussion on monitoring. Our focus will be on monitoring our cloud API usage for anomalies that could indicate that credentials have been stolen or are otherwise being abused. Now, in AWS, we can audit our API access logs using a service called CloudTrail. On this slide, we are enabling the CloudTrail service using Terraform code. Terraform is an infrastructure as code tool that we can use to configure our cloud environments. Its syntax is a fairly straightforward way of describing our cloud configuration, so we will use it to do so in a few of these slides. Now, Amazon is very strict about how they handle access management, so much so that CloudTrail can't even write to an S3 bucket on your behalf unless you authorize it with an IAM policy. So here's an example of such a policy provided by AWS's documentation, allowing for CloudTrail to write logs to your S3 bucket. Now, CloudTrails can be persisted to both S3 and CloudWatch. One of the advantages of using CloudWatch is now we can query our API audit logs using the same techniques that we did for flow logs. So here's an example of that right here. We are looking for decryption events in our AWS environment using a particular key. On to Azure. Unlike AWS, where we can enable all cloud API logs with a single resource, in Azure, we must enable logging on a service-by-service basis by creating what is called an Azure Monitor diagnostic setting. Google is like Azure in that you must enable logging for each service. In addition, you can choose to only log actions that read data or write data. However, by default, GCP logs have what are considered administrative actions logged at all times. These logs cannot be disabled. So if you're using GCP and you haven't yet audited your cloud logging configuration, rest assured that you at least have these critical logs at your disposal. But it's far from what you need in order to catch a potential attack. We're now going to show a potential attack or abuse of cryptographic keys and how to detect that abuse using Cloud API logging. In this demonstration, we're going to show you how to audit your Cloud API logs to find a misuse of a cryptographic key. A little bit of background here. The development team has decided to create their own custom solution for backing up their databases. They're not going to use the cloud native solutions that are provided. I wish they did, but instead they are using a manual process with MySQL dump. They're going to encrypt the database with KMS, and they're going to store it in S3. Same concept with Azure. They're going to dump the database. They are going to encrypt it using the Azure Key Vault, and then they're going to put the database in Azure Storage. And finally, with GCP, same thing, dump the database, KMS encrypt, and copy it to Google Cloud Storage. In this setup, we have run these scripts one time, so there shouldn't be a whole lot of activity with these cryptographic keys. Unfortunately, that is not the case. If we look at our key usage using Azure metrics, specifically our Key Vault metrics, we will see that there are a lot of events that are being triggered by our cryptographic keys, 6 within the past hour. If we look at the same thing with Google Cloud Storage, and we're going to specifically look for the backup key that we're using here, we will see a lot of traffic here as well. Much more traffic than we would have expected given our usage of the key. So why is this? Well, it turns out that a data scientist has actually been running a script of their own in order to decrypt the data in the database and run a variety of analytics. Now, this is unfortunately something that I've personally seen where data scientists, not given the data that they need to use to do their job, will find the data one way or the other. And oftentimes this will involve a lot of manual processes. They're going to run a variety of commands potentially on their workstation, and they're going to do some processing instead of perhaps getting the same data from an API or an SDK and using it securely. So in this instance, they are decrypting data from their workstation. And that's probably something we'd like to avoid. We would like to keep the usage of our cryptographic keys to our virtual private network. So this is something that we were able to find using our audit logs, but the solution is to lock down our keys such that they are not able to be used outside of our network and not by the wrong users. So just like before, we should compare the services at play here. AWS and Azure do not log anything by default when it comes to Cloud API audit logs. GCP also does not contain a lot of data that is useful to your organization, but at least they log what they consider to be admin actions. None of them log user actions by default, and the scope of these logs vary from provider to provider. The AWS logs you can enable for every single service with a single configuration. For Azure, you have to enable it on a service-by-service basis. And then GCP gets even more granular. You have to configure each service for a particular type of log. So this can help you save costs by limiting what you're logging, but it could also be more operationally expensive to enable all of these logs that you care about. Before we wrap up this conversation, let's talk about how we can use these metrics and logs in order to feed our alerting systems. Logs are valuable, but only if they are monitored. It is expensive to have human beings analyze all of your logs at all times, potentially impossible, depending on the size of your organization and the amount of data that you have. Luckily, we can help our incident response teams focus on interesting anomalies using alarms. Amazon CloudWatch has a service called CloudWatch Alarms for exactly this purpose. CloudWatch Alarms will perform an action when a CloudWatch metric exceeds a particular set of criteria. It is possible to use CloudWatch logs to create CloudWatch metrics. We can create a metric that counts every log that matches a particular pattern. From there, we can sound an alarm if this log occurs at a different rate than what we'd expect. Azure and GCP have similar capabilities to create an alert off of log-based metrics, but for the sake of time, we'll just show this example with AWS. This alarm will go off if on 2 separate occasions there are more than 80 decryption events in a period of 120 seconds. When the alarm goes off, we can deliver an alert to a variety of platforms via an SNS topic. By creating a variety of alarms for our cloud logs and metrics, we can sound the emergency alarm when things dramatically differ from the norm. So, what are your next steps? If you take nothing else away from this talk, please make sure that your organization is capturing Cloud API and network flow logs for each of the cloud providers that you use. It is impossible to start properly monitoring these environments unless you have data to analyze. Start collecting that data today. Next, take a look at what your organization is currently using for monitoring. Maybe you're already using cloud-based solutions. Great. Maybe you're using third-party solutions. Perhaps these third-party solutions are still useful in addition to cloud-based solutions. Maybe not. That's why you should use both in the medium term over the next 3 months. These cloud-based solutions can provide insights that you can't get otherwise. Combine your tools to maximize the chances that you'll find indicators of compromise. Long-term, you will discover several weaknesses in your cloud infrastructure and configuration. Work with engineering to harden your permissions using the principle of least privilege. If we can block attacks altogether, we absolutely should. However, monitoring and alerting will always be necessary to find the weaknesses we have not yet identified and fixed. Additionally, if you've determined that these cloud-based monitoring solutions are sufficient for your use cases, you might want to consider decommissioning redundant third-party solutions. Finally, while we can find a lot of anomalies simply by crafting log queries to find these anomalies, this will require some effort from your security and operations teams to understand the baseline, understand what is normal, and then craft queries that can find differences from those baselines. We can augment those efforts using machine learning. Dave Holzer, a faculty fellow at SANS, recently did a free live stream called Applying Machine Learning to Network Anomalies, which I've linked to here. So in summary, there are so many logs that your cloud providers can generate about your environment. But these logs are useless unless you are storing them and monitoring them. And in the process of storing and monitoring them, there are several key differences between the big three cloud providers, which you now understand and can help yourself navigate through. So I hope that you have enjoyed this presentation, and I hope that this has provided value to your organization. If you'd like to learn more about me and my teams, feel free to follow me and my teams on Twitter and LinkedIn. Wrapping up, I'd like to acknowledge a few folks who contributed to this presentation. First and foremost, thank you to Eric Johnson, the other author of Sec 510, without whom this course simply would not exist. Thanks to Frank Kim, my mentor at SANS, who has been instrumental in the development of this content. Make sure to check out Frank's presentation here at RSAC 2021. And thanks to everyone from Zoom who reviewed my presentation. I am proud that there are 2 other presentations at RSAC this year from Zoomies. Make sure to check out Max Krohn and Adam Rudderman's talks. And finally, this slide wouldn't be complete without me thanking you for listening. You had many high-quality talks to choose from today, and I really appreciate that you took the opportunity to attend mine. Thank you so much, and I hope you have a great rest of the conference.